Let's talk about one of the biggest, most mind-bending questions in all of physics. What is our universe actually made of? I mean, if you could zoom in way, way down, past the molecules, past the atoms, past the quarks, what is the very fabric of space and time itself?
Is reality smooth and continuous, like a movie film, or is it digital, made of tiny, fundamental pixels? This simple question, it turns out, is at the very heart of the biggest challenge in modern science, finding a single theory of quantum gravity. Because the answer, well, it changes everything.
Okay, to really get why this is such a huge deal, we need to look at our two current champions of physics, our two best ways of describing gravity, starting with the giants whose work we're all building on. For hundreds of years, Newton's idea was the law of the land. He saw gravity as this invisible force, a kinetic pull between any two objects with mass. But then along came Albert Einstein, and he just completely flipped the script. He said, no, gravity isn't a force at all. It's just geometry. His theory is kinematic. It says that the very shape of space-time tells objects how to move. Here's Einstein's beautiful idea, put simply. Think of space-time as a giant, stretchy trampoline. If you place a heavy bowling ball like our sun in the middle, it creates a deep curve. Now, if you roll a smaller marble, like the Earth, nearby, it doesn't get pulled by the bowling ball. It's just following the straightest possible path it can through the curved fabric. And that path is what physicists call a geodesic. It's a perfect explanation for why an astronaut in orbit feels weightless. They're in free fall. They aren't fighting against some invisible force. They're just coasting along their natural geodesic, following the curve of space-time around the Earth. So, Einstein's theory of general relativity is a masterpiece. It's basically perfect for describing everything on the large scale: planets, stars, entire galaxies. But, and this is a huge but, when you try to take this beautiful theory and shrink it down to the tiniest subatomic scales, it hits a massive brick wall. You see, right around the same time Einstein was rethinking the cosmos, another scientific revolution was taking off: quantum mechanics. And it described the bizarre world of tiny particles with stunning accuracy. The only problem? The two theories are totally, utterly, fundamentally incompatible. On one hand, you have general relativity's smooth, predictable, geometric universe. On the other hand, you have the quantum world, which is chunky, chaotic, and based on pure probability. They're like oil and water. When you try to plug quantum mechanics into Einstein's equations to describe gravity on a tiny scale, the math just it completely breaks. It spits out nonsense answers like infinity. This mathematical train wreck has a fancy name: non-renormalizability. But really, all that means is that it's a giant red flag from the universe, basically telling us, nope, your theory is incomplete. You're missing something really, really important. And that's why we need a new theory, a theory of quantum gravity. So if we can't just shrink Einstein's universe down to the quantum level, what's plan B? Well, this is where some physicists came up with a truly radical idea. What if, instead of trying to break down space-time, we try to build it up from scratch, using quantum rules right from the very start? And that brings us to this fascinating theory called causal dynamical triangulations. I know, it's a mouthful, so let's just call it CDT. The core idea of CDT is to throw out the whole idea of a smooth, pre-existing spacetime. Instead, it says, let's build the universe out of the simplest possible building blocks, like cosmic Legos. These cosmic Legos are called simplices, and a simplice is just the absolute simplest shape you can make in any dimension. So in 2 dimensions, it's a triangle. In 3 dimensions, a tetrahedron. And for our universe, which has 3 dimensions of space and 1 of time, CDT uses a 4-dimensional version of a triangle. The process itself is really elegant. You start with a pile of these tiny 4D shapes, and you give them a few simple rules for how they can be glued together. But here's the absolute key, the secret sauce. You enforce causality. You make it a non-negotiable rule that time only flows in one direction. There's always a before and an after. This one rule prevents all sorts of bizarre outcomes, like the universe folding back on itself. All right, so what happens when you let a supercomputer run wild with this? When it explores trillions upon trillions of possible ways these quantum Legos can click together following just those simple rules? Well, the researchers behind CDT discovered something absolutely stunning. It turns out there are basically 3 possible outcomes or phases for how the universe could turn out. 2 of them were, well, duds. In one phase, the universe just crumbles into a tiny, crumpled ball.
In another, it forms a weird, stringy thing with no real sense of time. But then there was phase C. And phase C was where the magic happened. Because inside this special region, this phase C, a universe just emerged. It spontaneously built itself out of the quantum chaos. And it wasn't just any universe, it was a stable, sprawling universe with 3 dimensions of space and 1 dimension of time. Sound familiar? It should. And here's the part that should give you goosebumps. The universe that just popped into existence in the computer didn't just have the right number of dimensions. Its overall shape, its large-scale geometry, it was a perfect match for something called a de Sitter universe, which is a known solution that comes directly from Einstein's own equations. Without being told to, the simulation had rediscovered Einstein's cosmos from the ground. This wasn't just a pretty picture either. The model was so robust that scientists could actually perform measurements on this simulated reality. Get this, they were even able to calculate the Planck length, the theoretical fundamental pixel size of our own universe. Finding this constant just pop out of the simulation was a huge sign that they were really onto something. So, where does all of this leave us? Let's go all the way back to that first question. Is our universe analog or digital? What is space-time, really? Well, CDT points to a pretty shocking answer. The smooth, continuous reality that we see and feel every day, it might just be a large-scale illusion. Space-time itself may not be the fundamental bedrock of reality. Instead, it could be an emergent property, something that arises from a deeper, more fundamental, and ultimately digital set of quantum rules. Which leaves us with this final, profound thought. Think about water. An individual H2O molecule isn't wet. It doesn't have the property of wetness, but you get enough of them together and wetness emerges. What if space-time is just like that? What if it isn't the fundamental stage on which the universe performs, but is actually one of the actors? An actor that emerges from the quantum bits themselves?